What is apparent viscosity? What is apparent viscosity? It is the ratio of viscosity equal to shear stress divided by rate of shear strain. Rate of shear strain. For Newtonian fluid. For Newtonian fluid, the apparent viscosity is constant. But for non-Newtonian fluid, apparent viscosity changes with respect to rate of shear strain. With respect to time, you can say. With respect to time. Understand? Now the topic is time dependent fluid. One number is rheopatic fluid. Rheopatic fluid, whose we know the shear stress. It is such fluid. In which apparent viscosity, both these time dependent fluids are non-Newtonian fluid. Apparent viscosity increases with respect to time. And the flow index greater than 1 for rheopatic. An example is rheopatic. For example, you can say and printer ink, printer ink. Next is gypsum paste, gypsum paste. And number 2 is thixotropic fluid. These also non-Newtonian fluids, and apparent viscosity decreases with respect to time, and flow index less than 1. And example is aqueous iron oxide gel. The next is pectin gel. These examples are very important for any government exam. And cream. And next is water and biotonite mixture. And you can see rheopatic fluids. For rheopatic fluid, after some days these are deep और गाढ़ा हो जाता है. After some days you can and this also apparent viscosity is increase. And apparent viscosity means this is the dynamic viscosity. Understand? Next, a problem. Calculate work done. In blowing a soft bubble of diameter 12 cm, and assume surface tension of soap 0.040 Newton meter. We know surface tension equal to force per unit length, or another is work done per unit area. We know surface tension equal to, for soap bubble number of free surface equal to 2, and suppose this is the spherical shape of soap bubble, and work done in contacting the free surface, this also delta L. So work done equal to surface tension into delta A, and here area equal to delta area equal to this total area for spherical 4 pi r square, and number of free surface is 2 equal to 4 pi r square, and d equal to diameter of soap 12 semi and radius equal to 6 semi or 0.06 meters, and the put work done equal to surface tension into area, and this is 8 pi r square, value is 0.06 whole square. Understand? So put the value of surface tension 0.040 and 8 pi into 0.06 whole square. So work done is 3.614 into 10 to the power minus 3 joule or Newton meter. Understand? Now this is the question. The velocity distribution of liquid is given as u equal to 5 into sine 5 pi y. Y is less than equal to 0.1 meter, and calculate the shear stress at wall, and where mu equal to dynamic viscosity equal 5 poise. Now we know suppose this is solid boundary, the solid boundary, and liquid is flowing, and this is the perpendicular direction of flow y, and the velocity distribution is this type. This is this type velocity distribution. This is u, this is y, and we know shear stress equal to mu into du by dy for at wall equal to y equal to 0, y equal to, and here mu equal to 5 poise. This is the CGS unit. Convert, this is the Pascal seconds. This is the SI units. And now the velocity distribution equal to 5 into sine 5 pi into y. So du by derivation with respect to y, 5 into 5 pi, this is the constant, and cos 5 pi y. Now du by dy y equal to 0, had y is cos value is 0 means 25 pi, this value is 1, অতএব 25 into pi. Understand? Now put the value in equation 1. Shear stress mu 0.5 into this 25 into pi. So the value is 39.27 Newton per meter square. Understand? Next topic is linearization of Newton's law of viscosity. Newton's law of viscosity. When fluid is flowing over a solid boundary, the velocity distribution is like that. This is the free stream velocity. Here at the near the solid boundary, this value is 0. This is no slip condition. But this is a solid boundary, and this is the another plates or something, and this is suppose any fluid, any kind of fluids. Here the velocity is 0, but this and this solid body, it's not moving, stationary, and this solid body is moving with v meter per seconds, and the velocity distribution is linearly. And near this solid boundary, fluid velocity of fluid near this solid boundary is 0, but velocity of fluids near this solid body, this moving solid body, is v. Understand? At this case, the shear stress equal to, we know, du by dy. So this is the viscosity of these fluids, and this one is moving v, and this one is 0, and these are apart h distance. So this is h. So for linearization of Newton's law of viscosity equal to mu into v by h. And this is first case, this is case 2, and first one was case 2, first one was case 1, and case 3, suppose case 3, suppose this is a half, suppose these are the this one is shaft, these are half this and between this surface there is any fluids, and here velocity is 0, but here velocity, this one is rotate in rpm. This is the side view of the shafts in rpm. And velocity of the fluid near these shafts is v, velocity of shaft, and the linear velocity of shaft is pi diameter of the shafts, pi dn by 60 meter per second. And you can get the value of velocity from the shafts and put the value here, and the height is h, and these are the, suppose these are the height between them, and put the value and get the next problem is the space between two parallel plates kept 3 meter apart is filled with oil of dynamic viscosity 0.2 Pascal per second. This is 3 meter. What is the shear stress as lower fixed plate if the upper one is moved with velocity 1.5 meters per second. Suppose this one is upper plate, this is the lower plate, these are fixed 0, and this plate is moving velocity v, this and this filled with oil